Good morning, everyone, and good morning, Professor. Our topic title is Adaptive Machine Learning Driven Regression Test Case Prioritization with Previous Defect Data and Code Change Impact Analysis. We are from Group 2, and myself, Swathi Nimala, and my colleagues are Mohan Venkata Sai Siddhana and Ram Vamshi Rudra. Let's see the introduction. Let's explore a critical aspect of modern software development regression testing. As many of you may know, regression testing serves as a safeguard for software projects, ensuring that modifications, whether they involve new features or bug fixes, don't advertently introduce new issues or regressions to previously working functionalities. In today's fast-paced development environments characterized by rapid development cycles and frequent updates, executing every single test case within a regression suite can become an impractical endeavor. Time and resource constraints limit our ability to perform exhaustive testing, pushing us towards strategies that are more efficient and effective. Traditional test case prioritization techniques often rely on static ranking models which may fail to capture the ever-evolving nature of software. They rank tests based on fixed criteria rather than tolerating them to the real-time state and history of the code base. Given these drawbacks, our discussion centers around the adaptive machine learning driven test case prioritization AML-RTCP approach, which emerges as a promising solution that combines historical defect data, real-time change analysis, and adaptive machine learning techniques to optimize the testing process. Now, let's see an example to understand the introduction better. Consider a banking application where new features are continuously added to the application. Without regression testing, a new feature could advertently break existing functionalities. Instead of running all test cases, resources could be directed to testing the modified parts of the application based on their impact, all thanks to AML-RTCP, Adaptive Machine Learning Driven Test Case Prioritization. Now, let's see the slide 2, which is the importance of prioritizing test cases. As we dive into test case prioritization, it's essential to understand why it matters so much. Prioritizing the execution of test cases allows teams to focus their efforts on the most critical areas of their code base, thereby maximizing the chances of quickly identifying defects. By prioritizing appropriately, we can minimize the risk of serious issues slipping through undetectable, which could harm users and damage the entire company's reputation as well. There are several traditional techniques we should consider. Among them, the first one is historical failure based. This technique assigns priority to test cases based on their historical records of failing. For example, if a certain module has repeatedly failed in past releases, tests associated with that module will be prioritized to run sooner. The next one is impact analysis of code changes. This method involves assessing any recent changes in the code and prioritizing the tests that are likely to be affected by those changes. If a function that handles users' authentication is modified, tests related to that login process will be prioritized to ensure that no regression occurs in this. critical functionality. And coming to the next one, static ranking models. These models are built on predetermined scores assigned to each test case based on fixed criteria, such as their complexity or historical failure rates. However, their static nature means they often responsiveness to real-time changes in the software environment. And coming to the next one, graph-based dependency analysis. This advanced method leverages a dependency graph to identify high-risk areas in the software. By mapping out dependencies, this approach allows teams to see which modules affect others and prioritizes tests accordingly. The last one, which is machine learning based approach. Emerging techniques in machine learning utilize various data driven strategies to predict potential defects in the software. For instance, defect prediction models can offer insights into which tests may fail based on historical patterns and code changes. Let's see an example to understand the importance of prioritizing test cases better. Let's say in an e-commerce platform, if testing shows that the payment processing module has a higher failure rate, tests related to that module will be prioritized after any code changes in the checkout process. In summary, effective prioritization is about combining these approaches to create a strategy that enhances the overall efficiency of the testing process. Let's see the challenges with traditional approaches. While traditional methods bring value, they are not without significant challenges that can hinder testing effectiveness and overall software quality. Static ranking models tend to struggle with adaptability. Software is dynamic, features change, and the code base evolves, and typically usage patterns may shift, making static ranking obsolete. This lack of flexibility can result in test cases that are no longer relevant being prioritized, wasting time and resources on ineffective testing. In continuous integration and deployment environments, testing becomes even more challenging due to the constant influx of changes. Here, executing all available test cases can become impractical as projects aim for speed and efficiency in delivering new features. Deciding which tests to run based on fixed priorities can introduce unnecessary delays. Additionally, many traditional methods heavily rely on past failure trends, while historical data can provide valuable insights. Relying solely on it can be detrimental, especially if the software has evolved significantly or if new types of defects are emerging that have not been observed in the past. These outdated reliance can lead to significant gaps in testing coverage. Let's say if a feature is updated frequently, a static ranking based on all failure trends might not accurately reflect the current risk or effectiveness of running specific tests. Now, I would like to say my own experience example to understand this concept better. When I worked in a software company, we used to do the upgrades and application fixes. So, whenever we install a new fix to the application, we know in which part the fix code is made for. For example, let's say the fix code is for the incoming files to the application. Now, Based on the previous failures, we know when we implement a new fix for the incoming files module, we know that we need to test that module first so that it will consume less time for the testing people, and also it will save resources and time. So likewise, based on the previous failures, we can estimate which testing needs to be done when we make a new fix. I hope you understood the example. Thank you so much, and my teammate will continue from here.
So the proposed framework addresses the limitations of traditional methods by offering a more dynamic, intelligent approach to test case ranking. The core objective of this framework is to establish a test case ranking system that is both fluid and responsive to real-time software changes. So drawing upon extensive historical defect data. By leveraging real-time analysis, this framework emphasizes the importance of adaptive learning in context of testing. Some of the key components of this innovative framework include historical defect data. So here it will analyze the historical defects, enables the teams to develop insights into which portions of code are inherently prone to bugs, guiding the prioritizations of tests linked to those models. Supervisor learning for defect prediction. By employing supervisor learning algorithms, the framework can predict potential defects based on historical matrices. So, training a model on past data enables it to generalize and make information predictions about future code changes. Deep learning for prioritization. So, what exactly it does? It will utilize the complex neural networks, allows for sophisticated pattern recognition, enabling the system to rank test cases based on multitude of factors dynamically. Real-time change impact analysis. So what exactly it does is it will continuously monitor of code changes, help to adjusting prioritization of test cases as they evolve, ensuring that efforts are directed towards the most critical areas needing the validation. Together, these components enhance the regressive testing process by making them more relevant, aligned with the current deployment context. So machine learning techniques. In this slide, we can say that the incorporation of advanced machine learning techniques within this framework serves as a cornerstone for optimizing test case prioritization. These techniques provide a data-backed up approach to predict and prioritize test cases more effectively than traditional methods. Predicting defects using supervisor learning is an integral part of this process. For instance, let's consider a software application that historically struggles with a specific model. By training a supervisor learning model using a past defect data, we can provide insights into areas that may need to rigorous testing due to their likelihood of encountering issues again. Models for ranking and future driven strategies. So it represents another exciting aspect of this approach. For example, hybrid architectures that utilize SST technologies combined with dynamic RAM could lead to more responsive testing. So the environments that manage resource utilization efficiently. Implementing these techniques allows us not only to understand memory uses better, but also to correlate testing strategies dynamically with their resource implications. So real-time change impact analysis. In this framework, real-time change impact analysis stands out as a transformative feature that ensures test cases are not only prioritized based on static dependencies but also dynamically adjusted in light of ongoing code changes. This analysis leverages dependency graphs to visualize how various components of code are interrelated. For example, if a function that handles crucial data transactions is changed, tests associated with that function will automatically receive high priority in execution schedule. This method also enhances efficiency, ensuring that important tests try to modify code are run first, thereby mitigating risks of potential failures in more critical parts of applications. Moreover, utilizing structural relationships and modification frequencies allows us to further refine our rank approaches. By continuously assessing changes and adjusting priorities accordingly, we can ensure our testing efforts are effectively aligned with evolving landscapes. Advantages of this framework. So, the implementation of this framework comes with several notable advantages that enhance the overall testing process. The first point is enhancing efficiency in fault detection. So, by focusing on a dynamic prioritization model, teams can identify potential defects earlier in the testing lifecycle. So, this is a key benefit as it enables rapid framework and facilitates quicker repairs before progressing to later stages of development. Shorter execution time. With the prioritized test case execution plan, the overall time spent on testing substantially decreases. As projects increasingly adopt CI/CD practices, there is a growing need for rapid testing cycles where speed and accuracy are paramount. Improvement of software quality. So, prioritizing high risk areas and techniques through this AML-RTCP enhances overall software quality. As team consistently identify and addresses defects sooner, and they also deliver more reliable software products to users. Flexibility in CI/CD environments. The dynamic nature of AML-RTCP accommodates the frequent changes associated with modern software development methodologies. By seamlessly adapting to these changes, teams maintain agility in testing, which is crucial for success in today's fast-paced tech landscape. So, by integrating these advantages, this AML-RTCP framework represents a significant leap forward in how we approach regression testing. Thank you.
Hello everyone, my name is Rambamshi. I'm going to explain about challenges and fixes. So at the beginning of new software project like where diving into a completely new domain, engineers face like a cold start problem. They lack historical data about past defects, which test cases found the most bugs, or how frequently elements of code break under certain conditions. Without this baseline, machine learning models have nothing to learn from. For this, we have fixes like borrow data from similar projects. Like if your organization has completed similar efforts before, you can after reuse or adapt the data. For example, let's say you have a standard approach for managing web applications. If you have the domain differs, tracking user login, payment profile pages. Patterns in how these areas break might be surprisingly transferable. And the second one is like generate synthetic data. When real data is you have like real data, you can simulate usage. Tools are like script can create pseudo random interactions mimicking user behavior or typical test scenarios. Two, not perfect synthetic data can at least train an initial model, helping it pick out basic patterns. And also continuous updates. Treat every test run, successful or not, as an opportunity to gather more reasons why a test succeeded or failed over time. You build a more accurate picture of your application week points and can retain or fine tune the machine learning model for better results. Coming to large data sets needed for accuracy. Here comes the challenge. Many AI or ML techniques, particularly deep learning data, to produce accurate predictions, you may need tens of thousands of millions of examples. But building a single massive data set for repeated test runs might seem out reach early on could be expensive in both time and effort. For this, we have fixes to focus on frequent or critical hotspots. Like rather than collecting data for every part of your application, zoom in on high risk areas models that change most frequently. This approach narrows your dataset scope but ensures that deep data density is higher when it matters most. And another fix is like leverage test results as a data source. Each new iteration, be it like a pull request test, add to your knowledge bank. Over time, the dataset grows naturally with minimal overhead. This incremental building approach is easier to manage and keeps your data relevant to the version of the software you are currently shipping. Now, coming to high resource usage challenge. Some advanced models, especially those involving in deep neural networks, can require immense computational power. They may slow down your training pipeline, leading to lengthy iteration cycles or high infrastructure cost. For this, we have fixes like first one is optimized hardware and cloud solution. If your organization can budget for specialized hardware like GPUs, TPUs, or AI-focused platforms, it can significantly speed up training and interference. Alternatively, cloud based solutions offer flexible pricing, scalable resources for particularly large workloads. And another fix is like simplify model architectures. Not every problem calls for a massive deep network. Sometimes architectures or traditional machine learning techniques are sufficient and still offer strong performance. And one more fix like model pruning. In case where deep learning is beneficial, you can prune or compress the train network by removing neurons or layers that contribute. This process reduces computational complexity and can make models more efficient to run. Coming to deep learning complexity, here comes a challenge. Building deep learning model is an art and a science. It typically requires specialized knowledge in tuning parameters. Like for this, we have fixes like start simple. Before jumping into complex architecture, try logistic regression or random forest or gradient boosting on your collected data. Many teams find these simpler approaches surprisingly effective for initial ranking tasks. And another one is like parallelization. If a deep network truly is necessary, parallelizing tasks across distributed system or breaking the data into smaller subsets can make the training process more manageable. And coming to auto machine learning tools, it is an another fix for this. Like modern auto machine learning solutions can handle tasks like hyperparameter turning automatically. Although it may not match the expertise of a seasoned data scientist in every scenario, it can provide a strong baseline without requiring specialized knowledge. And coming to the last one, model interpretability. And these like a high parameters model can seem like black boxes providing little insights into why a specific test might be a ranked higher. This can lead to disturb for stakeholders who want like a reasons behind the ranking decisions. For this, we have fixes like explanation tools. Techniques like local interpretable model agnostic explanations illustrate which inputs most affected the prediction. And the another one is opt for smaller transport models in case where interpretability is paramount. Simpler models like decision trees or rule-based assembles might sufficient. It's a trade-off. You might sacrifice some accuracy, but you gain transparency that your QA and development teams can easily validate. And there is an also another fix for this, like hybrid systems, combining data driven machine learning with explicit rule based logic that domain expertise can understand. This approach offers an intermediate solution, balancing the benefits of AI driven adaptability with clarity on certain code decisions. Now, coming to the future work, we have cross project learning, applying insights and patterns learned from one software project to another. This approach helps overcome limited data or low historical records in new environments, boosting model accuracy from the start. For this, like a possible approach like transfer learning and shared knowledge. For transfer learning, take a model that's been trained on one project and adapt it to another. And for shared knowledge, maintain a centralized repository of lessons learned so further projects benefit from past experience. Coming to the next one, further enhancements. It aimed to improve the current framework by combining machine learning with rule based methods. Hybrid models can sometimes be more flexible, interpretable, or easier to maintain than purely data driven approaches. Possible approach are like hybrid models, adaptive tuning. So coming to hybrid models, use rules or domain expertise to handle well-known scenarios, with letting machine learning tackle complex or unpredictable aspects. Now coming to adaptive tuning, it continuously refines both the analytical and deterministic components to keep pace with evolving project requirements. By cross project learning and exploring hybrid methodologies, organizations can achieve even more robust, scalable, and explainable approaches, ultimately fueling the continuous improvement of software testing and development process. And coming to the conclusion, it has flexible and dynamic ranking of test case. These has combining real-time analysis with sophisticated machine learning techniques, and also importance of contemporary software development methods. From all this, we go with like flexible and dynamic ranking of test case first. So modern regression testing framework require adaptability to changing code bases and defect patterns. By integrating machine learning and real-time impact analysis, teams can reorder their test suites to target the riskiest areas first. These continuous adjustments allows for more efficient use of resources while ensuring that new or frequent changing components receive the proper level of tuning, and also combining real-time analysis with sophisticated machine learning. Advanced models like LSTM network, boosted decision trees, and graph-based methods can detect shifting risk factors and structural changes in real time. This synergy between predictive and reactive analytics creates an agile testing environment, boosting overall fault detecting rates and reducing feedback loops in CI/CD pipelines. Importance of contemporary software development methods. As software evolves rapidly in iterative, continuous develop ecosystem, traditional static approaches to test prioritization are often insufficient. Embracing up to date practices such as dynamic ranking and incremental learning ensures that companies stay competitive by maintaining quality standards even under frequent releases and complex system architectures. By focusing on flexibility, real time insights, current development practices, software teams can achieve robust, efficient, and scalable test prioritization to consistently deliver high quality products. And we also have These are the references we have used in our presentation. Among all these, the first reference focused for our work in this presentation. And finally, thank you so much for listening our presentation. We hope this presentation gives you a good insights. Thank you.